Welcome back. As promised, we are going to cover a few other examples of feedback. I'll draw one more coupling diagram here, and then I encourage you to actually try to think of your own examples of feedback in preparation for the class period on Tuesday. So an additional example of a feedback is what some people would call the poverty trap. And as I'm drawing this coupling diagram and describing the process, think to yourself about whether this would be a positive or a negative feedback. So in the poverty trap, the basic idea is that poor people have less access to good education and fewer job opportunities, and therefore they remain poor. So we might define 3 different state variables to describe this system. One would be a person's level of income. Another that we've talked about would be their educational opportunities. And then finally, the third would be their job opportunities. So let's now resolve the connections or the couplings between these different state variables. As a person's income level goes up, his or her educational opportunities or their access to education and educational tools also tends to go up. This is in the same direction and is something that we could represent as a positive coupling with an arrow. And we could give this a value of +1. So as a person's educational opportunities increase, their job opportunities also tend to increase. So this would be another positive coupling with a red arrow and a +1. And as a person's job opportunities increase, their income level also tends to increase. So this would be a third +1. So we could think about the flip side. We were, after all, talking about the poverty trap. So as a person's, instead of thinking of a person's income level going up, we could also think about their income level going down. As their income level goes down, their access to educational opportunities also tends to go down. Again, this is in the same direction. Decreasing income leads to decreasing educational opportunities, so that results in a positive coupling here. So you could think about this whole cycle in the reverse direction. As their educational opportunities go down, their job opportunities also decrease. As their job opportunities decrease, their potential for earning a high income also decreases. And so all of these are in the same direction, and so they get +1s. So you know what to do next. And that is basically to go around the circle and take the product of these couplings. So here we have a +1 times another +1 times another +1. So this equals, of course, a +1. And so this is a positive feedback or a runaway feedback that traps people in poverty. Or at least leads to growing disparity between the haves and the have-nots, which has certainly been a big topic in this election cycle. So let's go through another example that's a little bit more relevant to Earth system science. And I want you, first of all, to take a look at this coupling diagram. I haven't drawn in arrows or circles, but I want you to try to figure out whether this is going to represent a positive or a negative feedback. So now the 3 state variables that we're talking about are the temperature of the Earth, the amount of carbon dioxide in the atmosphere, and the decomposition or burning rate of organic matter. So let's start, I think it makes sense to start with the decomposition or burning rate of organic matter. This is something that we're doing now as we're burning fossil fuels, which are, of course, very old organic matter. So as we burn this organic or decompose this organic matter, we increase the amount of carbon dioxide, which is in the atmosphere. And so we could represent this, let me undo that. We could represent this with an arrow. Okay, as the amount of carbon dioxide in the atmosphere goes up, we also expect the temperature of the Earth to go up. So again, we could represent this as an arrow, and I haven't forgotten to assign both of these +1s. So what happens to the decomposition or burning rate of organic matter as the temperature of the Earth goes up? Well, scientists, I don't expect you to know this in advance, but scientists generally have an understanding that as temperature increases, the decomposition rate of organic matter also increases, and the shape of this function looks exponential, a little bit like this. But obviously this is a positive coupling. As temperature increases, the decomposition rates increase. So even though it's not linear, we would assign it an arrow with a +1. So this, which we're depicting here, ends up being a positive feedback because we have a +1 times a +1 times another +1. So this is a positive or destabilizing feedback that's relevant to global warming. But one of the things you'll learn in this class is that Earth systems are complex, and this doesn't describe the whole story. So Earth's temperature actually affects countless processes, some of which are important and some of which are not so important. Here's another coupling diagram that, again, involves the temperature of the Earth, but a different set of state variables. Now we're looking at impacts of the temperature of the Earth on rates of plant growth and the amount of carbon dioxide in the atmosphere. So let's start here with temperature of the Earth. One of the things scientists know is that as the temperature of the Earth increases, plant growth also tends to increase. In part, this is because formerly glaciated areas are becoming deglaciated and are available for plant growth, but also in tropical areas, plants tend to grow faster when you give them warmer temperatures. And so we would represent this with a positive coupling and a +1. So what does the impact of plant growth have on carbon dioxide in the atmosphere? Should this be an arrow or a line that terminates in a circle? Well, plants photosynthesize, and photosynthesis is the process of the conversion of carbon dioxide in the atmosphere into plant tissue. So as plants grow faster, they remove more carbon dioxide from the atmosphere, and the amount of carbon dioxide in the atmosphere ends up going down. So an increase in plant growth leads to a decrease in carbon dioxide in the atmosphere, and we would then represent this as a negative coupling. So a negative coupling that looks like this. And we would give this a value of -1. And then we know this final arrow very well. As the amount of carbon dioxide in the atmosphere goes up, the temperature of the Earth also goes up. This is clearly a positive coupling, which we represent with a red arrow, and we assign a value of +1. So let's evaluate this feedback process now. So as we go around this loop, we have a +1 times a -1 times another +1, which this time gives us a -1. So +1 times -1 times +1 equals a -1. So this is a negative feedback or a stabilizing feedback. This particular feedback would actually tend to counter the effects of global warming and make it proceed at a slower rate. So stabilizing. Let's consider another example that is relevant to Earth system science. And now we're going to talk about melt ponds. So melt ponds are these features that you see here. This is a glaciated terrain, and there are portions of this glacier that are melting. Now, one of the big differences that you'll notice from the ice sheet and the melt ponds is that the melt ponds are very dark, whereas the ice sheets are very white. So do you remember the vocabulary word that we talked about in the beginning of this lecture that describes the reflectance or the darkness or brightness of features of the Earth's surface? So that vocabulary word is albedo. So that equals reflectance. And the snow here has very high albedo, whereas the melt ponds have a very low albedo. They're very dark. So let's consider the type of feedback that these melt ponds might be involved in. So I'm going to draw 3 boxes here, one of which is global ice abundance. The other of which is the albedo of the globe, so this is like an average albedo. And then the final one is global temperature. So as ice begins to melt, the albedo of the Earth's surface declines. So as ice abundance goes down, albedo goes down. Again, these are both in the same direction and should be represented as a positive coupling with a value of +1. So what effect does albedo have on global temperature? Well, just think about going outside on a hot day. Do you want to wear white or black? You actually want to wear white because that high albedo clothing is going to reflect more of the sun's incoming energy and is going to keep you cooler. So as albedo goes up, global temperature goes down, and this is a process, or this is an interaction that we should represent as a negative coupling. So a line with a circle at the end. And it gets, again, a value of -1. Okay, as global temperature goes down, ice abundance should go up. So again, these have opposite sign, and we would represent this, again, as a line with a circle at the end. It's a negative coupling that has a value of -1. So now let's evaluate this feedback cycle. So if we go around the feedback loop, we have a +1 times a -1 times another -1. -1 times a -1 equals a +1. So we have a +1 as the product, and this is a positive or destabilizing feedback. So now you've seen 3 different feedback processes involving Earth systems and global climate, 2 of which are positive and 1 of which is negative. And one of the things we'll be talking about later in this class is just how these different feedback processes interact with each other. This melt pond example here is another feedback that can lead to destabilization and very rapid changes in Earth's temperature. So we're going to move on and talk about equilibrium states. And equilibrium states are states that the system will not move from unless it is disturbed. So at equilibrium, the state of a system is not changing in time. We have stable equilibria and unstable equilibria. So a stable equilibrium characterizes the condition where if you perturb a system from that point, it will move back to it. This typically arises as a result of negative feedback loops or negative feedback cycles. An unstable equilibrium describes an equilibrium where once the system is displaced from that state, it moves away to a completely different state altogether. Positive feedback processes typically result in unstable equilibria. So we'll talk about an example of that when you come back to the next video.